say your name, English name, please. Go.
My name is Matthew,
Okay.
and today our group will introduce the physics in the flash. The first physics that I'm going to talk about is G-force. From Newton's second law of motion, we know that when an object's mass doesn't change with time, the force that it receives equals to its mass times its acceleration. In this scene, we can see that the flash ran towards Batman and stopped in about 1 second. We first assume that the flash mass is 70 kilograms, and his speed is 300 million meters per second because he runs in the speed of light. He stops in 1 second, so...
At the speed of the light?
Yes.
Is that assumed in the movie?
Yes.
Okay. But we can see it, right? We can see him.
Yeah, because he used slow motion when he runs in the speed of light in the movie.
Okay.
He decelerates to 0 meters per second in 1 second. So his acceleration is negative 300 million meters per second squared. From the value above, we can know that the force that he received is 21 billion newtons, which is more than 30 million G. And the G force that a human can tolerate without damaging our body in most cases is 9G vertically and 46G horizontally. It is impossible for the flash to stop in 1 second because the force that he received is way higher than how much human can tolerate, even if we take the highest record that a human survived. Okay. So in reality, the flash will be smashed into a flat board and suffer severe injury if he stops in such high deceleration.
What is that, 30 million G?
Yeah.
Oh, no, okay. Okay, that's good, Matthew. I give you homework. So, what kind of energy is needed to accelerate this guy, Matthew, or no Matthew, Flash, to the speed of the light? It's a homework.
Oh, okay, okay.
Okay, very good. Who's next?
Okay, I'm Ricky, and I want to talk about walk through the wall. And
what's the name? Jackie?
Ricky.
Ricky. Okay.
In the movie, we can see the Flash walk through the wall. In this video, we can see the Flash walk through the wall, but it is impossible in the real world, right? So I think there are two main points in this video about physics. First, the atomic structure of matter and repulsive forces, Coulomb force and Pauli exclusion principle. The Coulomb force is the atoms consist of positively charged nuclei and negatively charged electrons.
Yes.
And
Good.
when the atoms approach, the electrons will repulse by their charge. So they have Coulomb force. And Pauli exclusion principle is in the quantum mechanics. Electron obey this rule. So I think they are too low in this video. And the second is second law of thermodynamics. In this video, we can see the flash walk through the wall by vibration, and they have friction with the wall, and I think it will cause enormous heat, and the heat will fusion the wall. So I think it is impossible. And I calculate Coulomb force in this. Okay, and this is Coulomb force equation, and it is equals to 2.3. And the work is equals to that. And the mass of water, because our body, the flesh, the human's body is consists of most of water, and it's about 65%. And I just calculate the human's body, the human's water, body's water. Okay, so it is 2,000 moles water, and the total number of water molecules is about that, and each water molecule contains 10 electrons. One electron.
Your time is on. So can you
Okay, and total energy is about 3.5 times 10 powers to 11. So it is about 84 kilograms TNT power. So I think it is impossible.
So what did you calculate here?
Because electron and electron approach and apart, it will overcome some force, and we need to do some work to let them.
Okay, so this is the electronic potential energy of whole molecules, whole atoms in the human body, right? So you're calculating energy to destroy all of them, right? But you don't need to do that, right? What is the energy? What is the energy needed for this?
All of
Are you
our.
trying to go through the wall?
Yes, and
okay, you don't need to destroy humans to go through the wall, right?
Yes.
And then some of them are neutral, right? You don't need to destroy them. Okay, plus minus here is plus minus there, right? Plus minus here, there, right? So there's no force between them, right?
But
if all plus here, all minus here, yes, there's a force, right? You need to break.
yes.
But it's neutral, right? It's plus and minus, plus and minus. It's neutral. Please explain that in your report.
Okay.
Okay, this is very important. What is this number? Understanding, explain your criteria. Okay, next, please. But Vicky, I like you try to use the Coulomb force topic of the
I will talk about time paradox, and my name is Benson.
Benson, I remember.
And before I talk about the time paradox, I will introduce what is time. Yes. In what is time, then a lot of people have many ideas about the time, such as like Confucius journey. All that process is like a river. Yes. No. The time is like the river. The water flows. Yes. He thought the time is like the water flows, and the English poet said time and tide waits for no man. It is time is flowing. Time is flowing. Yes. In Leno's paradox says the soul if the sorry. Okay, 现在那个 if the error is stopped at every moment, like the error is stopped at any moment. So, but it moves. So it is paradox because it is stopped. It is stopped at any moment, but it moved. So it is the paradox, and the Leno doesn't fix the time it is. Okay. 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 And they talked about the theory of relative special relativity. The Einstein said that the time and some states will be some states will change and some states will be constant. Like the speed of light is a constant. It's like this. The speed of light is a constant. Yes. Okay. And according to Einstein's relative the special relativity, then we calculate the x prime is this, and y prime is y, and d prime is d, and t prime is this, and we have the Lorentz factor is this one is this one. Yes. Okay. When according to this, we can calculate whether we can use the over the speed of light to move on, like the hero in the movie. Yes, and we use the formula this t if the velocity of w is greater than the speed of light, we take the w equal 1.1c for example. Yes, and we take this into the time, and we calculate the time will be negative. Then
you finished?
yes.
Okay, what's the context to the movie?
Context.
You didn't expect, what are you talking about?
Because
What movie scene you're talking about?
because he moved over the speed of light. So I want to talk about
I thought he said the speed of the light. He traveled at the speed of the light, but it's over the speed of the light, which happens in a movie. You read or watched the movie?
I remember there has a thing like the flash is over the speed of light.
Okay, you need to explain that at the beginning, otherwise we don't understand the context. Right?
Sorry.
Okay, then how do you know speed of the light is a constant? Can you add it in the report? How do you know the speed of light is constant? Okay? Good. Okay, this is good. Okay, good job, guys. Okay, what's your name?
My name is UC, and I want to talk about the energy required for the flash to run and the friction force needed for him to stop.
This doesn't look like a speed of light. It's much slower.
Okay, in this scene, we can see the flash running at an incredible speed and then coming to a sudden stop.
Okay.
Do you ever curious about how he can do this? Now I want to calculate the energy required for him to run and the friction force needed for him to stop. To determine the Lorentz factor for the speed, we use the relativistic kinetic energy formula. We determine when the flash is at the 99% of the speed of light. And then we assume that the flash's mass is about 75 kilograms. Then we can find that he needs such a big number of the kinetic energy. And the kinetic energy that a normal 75 kilogram person needs while running per kilometer is this number. But the kinetic energy that the flash needs while he runs for a moment is such a bigger number. And we find that the energy needs for the flash is much more greater than the energy needs for the normal person. And then to calculate the friction force that's needed for the flash to come to an instant stop, we can use the energy that we previously calculated. And we assume that the distance for the flash to stop is very small. We approximate it as 0.1 meters. Then we can calculate the friction force needed for him to stop. Next. I assume because he's a small distance, and we find that he needs such a big number, but the 2011 Tohoku earthquake in Japan released energy equivalent to approximately this number of the energy. And we find that the flash stopping force is about 10,000 times greater than the energy released from the earthquake. So we can say that if the flash is coming to a sudden stop, then the whole Earth will shake with the flash. And so it is impossible for the flash to come to a sudden stop. Yes, and this is my report. Thank you.
Okay. So can you compare the energy of the flash to something in real life? Not the force, but then this energy. Yeah. NTHU.
This?
Yeah. Can you compare with something?
No.
Something in real life. Yeah.
This?
No. That you will find. Can you compare this for the energy in a real life?
In the what?
Real life.
Real life.
Real life.
Real life.
Yes. Like some battery
Okay.
or plant or something.
Okay.
Yeah.
Like bomb.
That's possible.
Okay.
But what's the time scale of this? So 35 kilometers per kilometer. So this is for 1 kilometer?
For yes.
And then
From
it's
for-
also for 1 kilometer?
Not just a moment, just if he want to.
It depends, right?
Yes.
So
Just
you
a
need to-
moment.
So you need to set this unit the
Okay.
same to compare.
Okay.
This is for a moment, right? But the runner is for kilometers.
So I can. Okay.
3 minutes or so, right?
Okay.
So the difference will be even larger.
Okay. Thank you.
Okay. Good. That was good.
My name is Jackie.
You are Jackie?
Yes.
Okay.
I'm talk about make a tornado in the video. Oh. Okay. He rotate his body and arm and make a tornado to as a weapon to blow his enemy into the sky. And okay, video is somehow error. Okay. See. Oh. Okay. Next page. So the tornado has the enough velocity in to provide enough kinetic energy to the enemy in the movie to blow to the sky. So I will introduce the forming condition for the normal tornado in the nature. Then we talk about in the movie. So the first is wind speed, and wind speed and its scale determine the power of this tornado. And the upward airflow and the low pressure in the center will help maintain the overall structure. Okay, and also other factors like humidity or the terrain will influence whether it forms in the nature. And in the movie, the Flash rotates body and arm to make a wind speed at least 18 meters per second, since he needs enough kinetic energy to blow a human being. Okay, so if you use the formula, okay, velocity equals to 2 times pi times radius times frequency, and the radius is also the length of his arm. Okay, so the frequency is about 2.8 or about 3 revolutions per second. So it sounds easier for the normal human to do that. But if you watch the movie, he creates a 2-meter high tornadoes. But when he rotates the body and arm, the swept area is actually only 0.1 meter width with his arm. So he need to do the same thing in a different height to make a uniform airflow vortex.
Okay.
So 2-meter height with his arm width with 0.1 meters, you need to do it 20 times as a single layer.
Really? So he doesn't
Rotated, yes.
Okay.
So the total number should do at least is 3 times 20, 60. And I don't know how normal person can tolerate. About maybe 10 revolutions per second is the maximum number. And he do it 6 times per second. Okay? That is my report.
Can you try to do it? How many times can you do that in 1 second?
I do it in the home, but headache and just dizzy. Oh, okay. Let's do that.
Or maybe 2. Thank you very much. Okay, good.
Okay.
Good, Jackie. Very good.
Okay,
Okay. Let's go to next.
Hi, I'm Thomas.
Thomas.
Yeah, can you please repeat? Right. Hi. Have sound.
It's okay. It's working.
Oh, it's okay. It's working. Okay, I will introduce the sonic boom. What is sonic boom? The sonic boom is a sound associated with a shock wave, and has an enormous amount of sun energy, and it is a continuous effect, and it affects only observed position, so, and a point of interact of geometric geometrical cone, just like this, and behind the object. And when when the object moves, the shape also moves behind it. And the physical of it well, the principle of it is when the object through the air, it will create some pressure wave in front of the object and behind it. It will come back with, it will compress when the velocity is increased. So it becomes a sonic boom like that. And why is it makes sonic boom? Because the flash speed is over the speed of the sound, so it made the sonic boom created is generated. So he will create a sonic boom when you run, and the sonic boom will cause some minor damage to sound schedule. So when he runs, he may cause damage to the ground or surrounding building. So maybe it's too exaggerated, but when he runs, it is impossible for for nothing to be free or not to be damaged. It will just cause many, just like this. Some damage or impact to other people or buildings. Yeah. That's all.
Okay. So he's running near the speed of the light, right?
Yeah.
So he's gonna create the
Sonic.
challenge of light too, right? So can you calculate what kind of challenge of light he's gonna create in your report?
Okay.
Okay. It's better if you can, like others are doing, you calculate the energy of this sonic boom. That would be better. Next
Yeah.
time.
Okay.
Okay. Thank you, Thomas.
Thanks, teacher.
Okay. And then Danny.
And I'm Danny, and I will be introduce about the lightning. This video.快转。OK， 下一页，下一页。And in this video, and the Superwoman is pick the flash up to sky and let him hit the lightning and make him get the superpower again. And I think it is impossible in physics because the lightning is have many strong energies to kill the human, and because in this time the Flash is not have the superpower, and the voltage of the lightning is about 1 million volts, and the resistance of the human is about 100,000 ohms, and you can know by the ohms laws, the current which passing through the human body is about 10 amperes because I equal V over R. And but the maximum current that the human body can tolerate is about 0.2 ampere, and it is smaller than the 10 ampere more. And the flash is wet from the rain, and the surface when the surface is wet, that will decrease the resistance of heat. So the according to the Ohm's laws, the current that at the flash body is more than 10 amperes. Okay. And according to the Joule's law, the surface of the flashes will be generate more than 10 million joules of heat, and the energy is enough to turn him into a barbecue. And this is the formula that Q equal I ping pong. And you know?
No, I don't know.
This formula,
What
yes,
is I? What is I?
I is current.
Okay. What is R? What is
R is the resistance.
You are still
Okay. How? Okay.
okay. So you finish?
Yeah, I finished.
Okay. What happens to the resistance when he gets wet?
Decrease.
Yeah, how much?
Mm,
Okay, please calculate the energy when he's wet in your book. Okay? Okay, good. Then we go to quiz, right?
yeah.
Okay. Good. You guys are keeping time. So everyone please join a couple quiz. You guys have cell phones, I think, right? This one guy I didn't give the homework. Who didn't get the homework? You? Can you calculate which, don't look at others. Can you calculate? So you guys talk about flash, right? And here's Iron Man, right? So can you calculate which is stronger, flash or Iron Man? Just calculate and compare which is stronger. Iron Man, someone talk about it. No, I think it's clear. Isn't that Iron Man that the suit and that's Iron Man. No, that was Iron Man. Anyway, everybody join. Who needs more time? If you're not joining, do you know how to use internet? Okay.
Okay.
No, is it okay? Okay. Okay, let's get started.
Okay.
it is very easy, right? My only
Oh, I don't know, it's good count. How come?
So the reason why we can tolerate less G-force vertically is because when the force is parallel to our spine, our body are not good at handling it. Yes, like pilots, jet pilots can.
Okay, is 75 kilocalories. This is different. That one is correct. Okay. Okay.
Diagram again? Okay. You guys need to work harder to beat this guy. Okay. So this Superman Oh, Superman. Who's Superman? Wait. You cannot join. You're in the team. Okay, this is a program because you knocked out someone who really is third grade. We don't know who gets the point, right? You don't get the point, but then number 4 you get a point. So we cannot do that. Every week we're doing this, right? Okay. Thank you very much. Any comments? It's okay.
Okay.
It's okay.
Thank you.
Next team, please prepare.